Problem 1.15 asks us to estimate the average temperature of the air inside a hot air balloon, assuming that the total mass of the unfilled balloon in the payload is 500 kilograms, and it also asks us to find what the mass of the air inside the balloon is. To begin, we see that there are two forces acting on the balloon, the upward buoyant force and gravity. The buoyant force can be written as rho naught times the volume times gravity, where rho naught is the density of air outside of the balloon, and this should be approximately equal to the force of gravity, which can be written as the combination of the mass of the balloon and its cargo plus the mass of the air inside the balloon, written as little m times g. Now that we have this equation, we can rewrite little m as the density of the air inside, or rho I, times the volume. Then, plugging this in and doing some algebra, we get the final equation rho naught minus rho I equals the mass over the volume. Now I want to find rho in terms of pressure and temperature. To do so, we're going to start by assuming that we are dealing with an ideal gas, so we can use the ideal gas law, which is pressure times volume equals the number of atoms times Boltzmann constant times temperature. Finally, I want to solve that for n. Now I want to write the density equation as the number of atoms times the mass of each atom over volume. Then, if we plug in what we had previously found for n, we get the new equation, which is the mass of the air molecules times the pressure divided by Boltzmann's constant times the temperature. We can now use the previous two equations we solved for to combine them together to get the third equation we see here. Since the balloon is not sealed, we know that the pressure of the air outside and the pressure of the air inside must be equal. This means that we can now pull out the mass, pressure, and Boltzmann constant from both of the left side terms and divide it out to the right side. We can then move the temperature outside term over to the right and solve so that we get just an equation for the temperature inside of the balloon. Now that we have an equation for the temperature of the air inside the balloon, we can begin to plug in our values. To start, we will assume the balloon to have a radius of about 7 meters. If we do this, we can plug in volume as 4/3 pi r cubed. For the temperature, we will use 290 degrees Kelvin. For the mass of an air molecule, we will have 4.8 times 10 to the negative 26 kilograms. We are given that the mass of the entire system is 500 kilograms. The Boltzmann constant will also be plugged in, and for pressure, we will use standard pressure of 10 to the 5th newtons per meter squared. All of this together gives us a final internal temperature of the balloon of 408.25 degrees Kelvin. And this is plausible due to the fact that the air inside would need to be warmer in order to have a lower density to allow it to have an upward buoyant force. Finally, we need to solve for the mass of the air inside of the balloon. We can write the mass of the air as the number of particles inside of the balloon times the mass of each particle. Previously, we had already solved for the number of particles within the balloon, so we can plug that in for our n and use our previous values that we used before, as well as our new temperature we found for the air inside the balloon. And this will give us a result of 1,226 kilograms for the mass of the air inside of the balloon.